devices. The other thing that we are particularly interested in is chemical stability of your material, your choice of your material that you use in your TV screens. I'm just showing you some examples here. It's a green phosphor. This is before applications. So after some times, the phosphor is going to degrade. So we study the mechanism of degradation. There's a lot of chemical changes that appear on the surface. So another examples, we have chemical surface appearing, taking place on the surface, which lead to the degradation of your material. But we are creating phosphors, we are preparing phosphor which are chemically stable, which do not degrade like these other ones here. So remember, every time you get a good phosphor, you get a better performance of your display or your light emitting device. So I want to take you through the LED lighting, which I think today we are trying to replace these lights with the LED lights. Remember, we have what we call a three-color system, where we combine red, green, and blue light in order to get white light. The problem with this is expensive. So the second generation was we still use phosphorus in this, but in this case now we mix blue LED with a yellow light from phosphor coatings, and then we still get red light. So this has reduced the cost, but it's still expensive. But now what we are trying to do is to create a single phosphorus where we can only have one LED, and then we have this phosphor which is emitting white light. So this will be cost effective. We want to get this at cost effectively, but without compromising the efficiency. So I'm just showing you some example of the phosphors that we have made. We mixed aluminates and silicates here. You can have two metal ions, mixing them together. So by mixing them together, you can in fact tune the emission color of your material. For example, if you look at terbium, it emits green normally, but now there are chances that you can get blue, you can also get red. So this is an example of a material where you can actually get red, green, and blue simultaneously, and then you have one host phosphor. So but how do you achieve that? By mixing all this, we're able to come up with a ratio of calcium to strontium, 0:3 and 0:7. And then in that case, we're able to reduce the green emission, but at the same time, we're able to increase the blue emission. You will see in the next slides. This is terbium. It's emitting both blue and green simultaneously. So we wanted to improve the red emission, but it was a challenge for us. So what we did is we took another rare earth, which we combine in one system. So you have terbium and europium. So they are emitting, terbium is emitting green and blue, while europium is emitting red. So you have red, green, and blue simultaneously, and together now you can get white light from one common host. So this, it's actually, it was a good observation from our laboratory. This can, in the future, be used in LED lighting. So I just want to compare the fluorescent lamps with the LED lamps here. The ones that we are using currently here, they have short lifespan. They have mercury, which means if one of these breaks, we will have to leave this room because mercury is going to be liberated and it's a harmful gas. But now if you look at the LEDs, we don't use mercury, so they are environmentally friendly. We use less energy, and then the light is also directional. They are 30% more efficient than the ones that we have here. The other thing is that the LED bulbs, they don't liberate heat like the ones that we have here. What is the point of us having these ones here where we are going to liberate heat? We are going to need air conditioner at the same time. We use more energy. So if we use these ones, they use cold cathodes, no heat is liberated. So if we can get a phosphor that can be used in this one, it will be a breakthrough for us. So another application of phosphors in renewable energy, solar cells. We know in South Africa we use nuclear and coal energy. More than 90% of electricity comes from coal-fired power plants. What are the disadvantages? It's exhaust stability, they cause global warming, environmentally unfriendly. Also, to dispose of nuclear waste is a challenge. So what will be the possible solution is to resort to solar energy. So we are also doing some work on solar energy. We prepare phosphors that can be used in silicon solar cells. We prepare phosphors that can be used in organic solar cells. We also have another generation of solar cells, thin film solar cells, which I'm not going to talk about in my